Okay, that's recorded. Just need to make sure because. So. First of all, sorry about messing up the recording on Tuesday. I don't know exactly what mistake I made, but I screwed something up and it didn't record properly. So I put up together one edited together from footage from last year, covering the same material. So worksheets 8 through 12 will be due on the 7th, October 7th. Homework number 2 was also due on October 7th. And our second test will be on October 7th. I'm quite started on fully putting it together, but it should be similar to the last one, 60 questions, multiple choice on those chapters. I need to go through and edit an older one. That's October 7th is not next Tuesday, but the week after. And we're gonna finish chapter 11 and start chapter 12 today, and we should probably finish chapter 12 next Tuesday. And that'll be the material we're covering. So we're a little bit ahead of schedule. All right. So we'll see where we end up with that. So let's talk about the structures of the outer planets. So the outer planets are different than the inner planets. The outer planets, are far from the sun, so they're very cold. They're very large in size and mass because they're big enough to hold on to gas. They're low density because it's gas. And because they're big, they all rotate quickly. It turns out larger planets tend to rotate faster. All of them have a large number of moons. At the moment, as far as we know, Saturn has the most, followed by Jupiter, and then Uranus and Neptune both have identified a bit over a dozen, around 15 each. But Saturn has like 150, Jupiter has 90 something, and we just don't have the numbers on the other ones because we haven't visited them as much. So there's probably more moons we haven't identified around Uranus and Neptune. But known moons, Uranus and Neptune both have about 15 each. I think I'll get to the number later. And they all have a ring system. Again, Saturn's is the most impressive. Jupiter has very faint, dusty rings. And Uranus and Neptune's rings are dark. They're made of darker material. Saturn's rings are made of ice primarily, while Uranus and Neptune's rings are more like sooty or darker colored things, so they're harder to see. And Neptune's rings are a little more irregular. So they're larger, they're much less dense. Saturn is the least dense, as it's less dense than water on average. Here's a table of properties that you can look at in your own time. You can see that they all have reasonable magnetic fields. Jupiter has a very strong magnetic field. Saturn, Uranus, and Neptune all have weaker magnetic fields. They're relatively cold, as you can see here, and they're not very dense, but their gravities are all, a bit stronger than Earth, generally. So the Jovian planets compared to Earth, you can see they're all the Jovian planets are quite a bit bigger than Earth. And Saturn is less dense than water, so if you could float it in a bathtub, it would float. Now, the Jovian planets are basically come in two types. Jupiter and Saturn are both very similar to each other. They're primarily gaseous and liquid hydrogen, with a layer of liquid metallic hydrogen below that, which is what generates their magnetic fields. While the interior of Uranus and Neptune is sort of an icy slush, and their magnetic field is generated in a different manner. And this can be observed by the fact that the magnetic fields of Uranus and Neptune aren't well aligned with their rotation, and they aren't centered on the center of the planet. They're off center and at weird angles. So Jupiter has a rock or ice core, a thick layer of liquid metallic hydrogen. So hydrogen, if you put it under enough pressure, becomes metallic. So electrical current can flow through it. And we've made this in the lab, but it takes enormous pressures. Which is why only why only Jupiter and Saturn have these layers of liquid metallic hydrogen. Above the liquid metallic hydrogen, there's a liquid hydrogen layer. And then above that, there's a gaseous hydrogen atmosphere. And when you have a conducting liquid in a spinning planet, you get a magnetic field. On Earth, that magnetic field is generated by the liquid metal portion of our core. On Jupiter, it's generated by the metallic hydrogen portion as Jupiter spins. So this is Jupiter, cut through. You can see aurora up above. So there's no direct information about Jupiter's interior, but we do know its components quite well because the Galileo probe entered the atmosphere and sampled the atmosphere, so we know what the atmosphere is made. Its main components, hydrogen and helium, are well understood. There's a lot of research into hydrogen and helium. Speaking personally, I've done some of it. My PhD was on effects in solid helium, so not the sort of thing you see in planets because I was dealing with very low temperatures, but yeah, there's a lot of research done. And so it's thought to have a rocky core, a layer of liquid metallic hydrogen, which again, we've created metallic hydrogen in the lab, but it takes enormous pressures, so it's hard. And a layer of molecular hydrogen above, liquid hydrogen, and then gaseous hydrogen above. And helium doesn't do much. So the helium is interspersed throughout, but the helium is not going to do a lot because it's a noble gas and it's very happy on its own. But Saturn is very similar to Jupiter, except it has less liquid metallic hydrogen. It's smaller, so the pressures aren't as high, so it has less liquid metallic hydrogen. But otherwise, the layers are all more or less the same. Rocky core, liquid metallic hydrogen, liquid hydrogen, gaseous hydrogen, helium. And similarly, there's helium interspersed throughout the whole thing. Uranus and Neptune are thought to have a rocky core and a thick icy mantle that's like made of water, ammonia, and methane ices, and it's sort of slushy. And then a gaseous atmosphere and maybe a thin layer of liquid hydrogen and helium above. But there's a lot more methane in their atmospheres. So if we compare the internal structure of Uranus and Neptune to the structures of Jupiter and Saturn. So here's Jupiter and Saturn. You can see Saturn has significantly less metallic hydrogen, while Uranus and Neptune have a rocky core, a layer of slush, and then molecular hydrogen above that. So Uranus is also odd because it's tilted on its side. Something happened that caused it to be tilted on its side. So its axis of rotation lies almost in the plane of its orbit. And that means it has the most extreme seasons of any planet. because, you know, it's northern winter solstice. Basically, the entire northern hemisphere is pointing away from the sun, while the southern hemisphere is pointing directly at it. It's tilted so much, it has really dramatic effects from the tilt in theory. It's very far from the sun, so that reduces the effects a little bit. And the whole cycle is some, now, years. So the equatorial regions of 2 summers at the 2 equinoxes, 42 years apart, and 2 winters at the solstices, falls plunged into darkness also for 42 years at the time. So most of the Jovian planets have significant internal heat sources. They still have leftover heat from their formation that's heating them from within. This is what drives a lot of their weather, because they are so far from the sun, they don't get a lot of heat from the sun. They give off more energy than they receive from the sun. That's sort of the definition of a significant internal heat source. This is leftover energy from their formation or energy from their differentiation. You know, as they formed and glommed together, they heated up. And then as they differentiated with a heavier stuff sunk to the middle, that had friction and warmed things up as well. The odd one out is Uranus. Neptune has a source of internal energy, but Uranus does not. It's not totally well understood, but it's thought that possibly there's some relation to the effects that made Uranus's, rotation so odd. It could have gotten more disrupted and lost more energy that way. All of the Jovian planets have magnetic fields. Jupiter has the strongest magnetic field of any of the planets. It's generated by currents in the liquid metallic hydrogen. And that magnetic field is in fact so large that the magnetic field of any planet, the area dominated by that magnetic field, gets stretched by the interacting with the solar wind, because the sun is constantly spewing out charged particles, and those run into the magnetic field, and because they're charged particles, their movement generates magnetic fields, and their interaction with the magnetic field distorts the magnetic field. So basically there's a bow wave at the front, and then the backside trails off behind. So this happens with Earth, this happens with all the planets that have magnetic fields. The trailing end of Jupiter's magnetic field is so big and so long, it actually passes the orbit of Saturn. So we're sending a probe to Saturn, and it passed into the area covered by Jupiter's magnetic field while it was beyond the orbit of Saturn. So you also get auroras on Jupiter, as you can see here. Any planet with a magnetic field in an atmosphere will have auroras, because auroras are just caused by solar wind particles being redirected by the magnetic field and slamming into the atmosphere in a concentrated way. So they happen on Earth, they happen on Jupiter, as you can see here. Saturn, because it has less metallic hydrogen, has a weaker magnetic field. And the magnetic fields of Uranus and Neptune, they both have magnetic fields that are significant, but they come from a different source. They're very strange when they're looked at. The magnetic fields of Uranus and Neptune so most of the magnetic fields are aligned with the rotation of the planet because they're generated by the spinning of the liquid portion, the currents in the spinning liquid portion. The spinning of the planet helps generate the magnetic field. So they're generally aligned with the direction of the planet's rotation. They might be off by a little bit, but they're not hugely off. They're like within 10-ish degrees or so. Uranus and Neptune are both not aligned with the axis of rotation, so they're off by like 30, 40 degrees or more, I don't remember the exact numbers. They're also not aligned with the center of the planet. They're off center. And they're not aligned with the rotation. Well, I don't know what happened here, but we will watch this on YouTube.
A magnetosphere is the sphere of influence of a magnetic field. So a planet that has a magnetic field has a magnetosphere when its sphere of influence extends beyond the planet out into space and affects the region around it.
The presence of the Earth's magnetic field was
Yes, you have a question? This is 11. Chapter 11 is on the outer planets. Chapter 12 is on kind of etc. Moons, Plutoids, other stuff.
recognized back in the 14th or 15th century, and since the 17th century, it's been a topic of active study. Yet we still don't really know how magnetic fields are generated inside planets.
The magnetosphere of Jupiter is vast. So if you think of Jupiter being 10 times the size of the Earth, and the magnetosphere is 100 times the size of Jupiter. So this is vast, a big, big, big volume.
By measuring Jupiter's magnetic field from Juno, we hope to do two things. One is to advance our understanding of how magnetic fields are generated in planets, and the other is to learn about the interior structure of Jupiter. You might question why go 400 million miles to Jupiter to study its magnetic field when the Earth has a perfectly good magnetic field which we could study. Jupiter's metallic hydrogen core is much closer to the surface, so when we measure Jupiter's magnetic field from Juno, we're much closer to where the magnetic field is generated, and by looking at the magnetic field, we should be able to tell whether Jupiter has a solid inner core, and that has profound consequences for how Jupiter formed, for models of its interior, for understanding its gravity field. It's a sort of key observation we'd like to pin down for Jupiter.
So, yeah, I hope. So as mentioned, here's another video. I don't know what's up with this video player configuration error. Let's try this again. Nope. Well, they open just fine here.
Magnetic fields have been a curiosity for thousands of years. And so, of course, we know now that magnetic fields are generated by what's called dynamo action, the convective motion of an electrically conducting fluid. Even though we can map the Earth's magnetic field with extraordinary accuracy with satellites in orbit about the Earth, the one thing we can't do is see clearly through all the crustal magnetization that is right beneath our feet. Jupiter is a gaseous planet, hydrogen, helium. There is no magnetized crust that obscures our view of the dynamo deep below. So the exciting part about the Jupiter mission is that we'll be able to image for the first time the magnetic field on the dynamo surface in a way that would never ever be possible on Earth. Jupiter is also the planet with the largest magnetic field. Its magnetosphere is huge. If you were to look up into the night sky, and if you could see the outline of its magnetosphere, which you can't, it would be about the size of the moon in the sky. It's a very, very large magnetosphere. In fact, in the Voyager program, we learned that the magnetic tail, the part of the magnetosphere that is drawn away from the sun, extends all the way out to the orbit of Saturn and in all likelihood beyond. It's a very large feature in our solar system. It's a pity we can't see it. Juno's the fastest spacecraft ever to venture into the outer solar system. It's the first to orbit pole to pole about Jupiter, and it's the most heavily shielded spacecraft that we've ever launched. The mission is designed to basically wrap Jupiter in a dense net of observations, completely covering the sphere. So to do that, we need a polar orbit, one that passes over the North Pole, along a line of longitude, and over the South Pole. And we do this over the 37 orbits of the nominal mission, and by the time we're done, we've got orbits separated in longitude by about every 12 degrees. So we completely cover the sphere. A magnetometer is, it's best to think of it as a fancy compass. Unlike a compass that just records the direction of the magnetic field, our instrument tells you both what direction the field is in and what the magnitude is. And we can measure that very, very accurately to 100 parts per million. Juno's magnetometer is another in a long line of magnetometers built here at Goddard Space Flight Center, following designs developed by Mario Acuna years ago. Our instrument is between 1 and 2 orders of magnitude more accurate than anything that's flown to Jupiter before. And of course, part of that is the result of the star cameras that we're able to fly with our sensors so that we can determine the absolute orientation in space of these sensors. If we did not know the orientation of the sensor as well as we can determine it with the star cameras, we would lose accuracy in the vector measurement. So we carry 4 star cameras with our 2 magnetometer sensors. These have to be held in the same orientation with respect to each other under very extreme environmental conditions. So we designed what we call a magnetometer optical bench. It's a special structure about a square foot in size that is made of a carbon silicon carbide material, almost impossible to machine. But once it's fabricated and the sensors are assembled, they act as one. And that's one of the reasons why we can achieve much higher accuracy than has ever been attempted before. We hope to learn more about how a magnetic field is generated by dynamo action deep in a planet's interior. For me, the great excitement is the opportunity to look down and get the first clear, unobstructed view of what the magnetic field looks like on the surface of a dynamo where it's generated. It's always incredible to be the first person in the world to see anything. We stand to be the first to be able to look down upon the dynamo and see it clearly for the first time.
So, Jupiter's magnetosphere, the intrinsic field strength is something like 20,000 times that of Earth's. And the magnetosphere can extend even beyond the orbit of Saturn. So it was detected by Voyager and the Pioneer probes. That magnetosphere extends beyond the orbit of Saturn. Jupiter, because it has a magnetic field, particles from the solar wind get redirected to the poles and we get auroras. And they have the exact same cause as auroras on Earth. Particles from the solar wind being redirected from the poles towards the poles and slamming into the atmosphere. Uranus and Neptune have weirdly angled magnetic fields that are off center. So here you can see this is Uranus. Its magnetic field is off from the direction of its rotation by like almost 60 degrees, and it's a third of the radius off center. It doesn't even pass through the center of the planet. So yeah, Uranus is off by 60 degrees and off center by like a third of a radius. Neptune's is off by 46 degrees, something like that, and is also significantly off center. They both have substantial magnetic fields, but have a large axis, angle to their rotation axis. And these angles show where a bar magnet would be. So, that would produce a similar field. So you'll notice that Uranus and Neptune are both significantly off center. You can see Saturn, Jupiter, and Earth all are centered and within about 10, Jupiter's off by 10 degrees, Earth is off by 11. They're within about 10 degrees of, and Saturn is basically aligned of the axis of rotation, not 60 or 47, This is more than an eighth of a circle. This is a sixth of the circle. Wow, that's significant. The Jovian planets are divided into two distinct groups: the liquid gas giants, which are Jupiter and Saturn, and the ice giants. That's Uranus and Neptune, because of their internal structure. So again, the Uranus and Neptune have a core of ice, while Jupiter and Saturn have a core of liquid metallic hydrogen. Most of the Jovian planets have some source of internal heat, and all Jovian planets have a magnetic field, but the magnetic field of Jupiter and Saturn is formed by a different process than the magnetic field of Uranus and Neptune. Which is why Uranus and Neptune's magnetic fields are off-center and at a weird angle. Let's talk about their atmospheres. In general, their atmospheres are primarily hydrogen and helium. They also have some hydrogen compounds in them: water vapor, methane, ammonia. The Galileo spacecraft was sent to Jupiter to probe as a probe to study the atmosphere. So we know the composition of Jupiter's atmosphere very well, because we dropped a probe in there to analyze it. So the atmospheric structure of Jupiter, it has what you're seeing here are clouds in the atmosphere, because hydrogen gas is effectively invisible. It's just a transparent gas. So you're seeing clouds in the atmosphere. The lighter colored zones are higher in the atmosphere. Those are clouds of ammonia. While the darker colored belts, lower in the atmosphere, I believe those are sulfur compounds, like hydrogen sulfide. So bright zones and darker belts. The zones are cooler and higher than the belts. There's a stable flow that underlies the zones and bands called zonal flow. And this is a sort of simplified model. At the zones, stuff is coming up. At the belts, stuff is sinking down. And there are, alternating flows in between them. So this is the structure of hydrogen. It's thought that there's ammonia clouds on top, ammonium hydrosulfide clouds below that, which are probably the browns, and then water clouds below those. So ammonia ice forming clouds, ammonium hydrosulfide ice forming clouds below that, and then water ice below that. It has no solid surface. We take the top of the troposphere to be 0 kilometers. So the clouds are below the 0 altitude. The lowest cloud layer can't be seen by optical telescopes, but measurements by the Galileo probe show high wind speeds even at great depth, probably due to heating from the planet and not from the sun. So on Earth, these cycles are driven by heat from the sun. On Jupiter and such, there's probably more of an effect lower down, driven by heating from the planet than the sun, especially because the planet is giving off more heat than it's receiving from the sun. So the Galileo probe descended into Jupiter's atmosphere and sent back valuable data. It descended in here. It did not come out, but it sent back data. Saturn has less distinct cloud bands. It's further from the sun, so it's cooler. Its gravity is a bit weaker because it's smaller and less dense, and subsequently less dense. So its cloud layers are thicker, so it has less distinct cloud bands. The bands are less distinct. Because of the thicker atmosphere, so you're only just seeing the top layer. Somewhat colder, its atmosphere is thicker, its bands are fainter because of that. The pressure is lower, it has 3 cloud layers. Again, ammonia ice, ammonium hydrosulfide ice, and water ice. Because the cloud layers are thicker than on Jupiter, we only see the top layer. So we see a lot less color variation. Uranus, and very boring one. It's nearly featureless atmosphere. It has a stable atmosphere. It has no real internal heat source, so it's very stable. It doesn't change much. You get a nearly featureless ball. Both Uranus and Neptune are blue because of the significant quantity of methane in their atmosphere, which absorbs red light and scatters blue. Neptune. So you can observe the rotation of Uranus by looking at storms as it rotates, because there is some weather. It's just minimal compared to the other planets. And then we have here Neptune, also blue because of the methane in the atmosphere. It does have an internal heat source, has very high winds, had at least for a while a great giant storm as a great dark spot, but that has subsequently gone away. It was observed by Voyager, but then later observations from Hubble showed it fading away. And the atmosphere of so Uranus and Neptune, the upper atmosphere is dominated by methane clouds. And it's thought that maybe there's hydrogen sulfide ones underneath, but it's not so well known because they're less well studied than Jupiter and Saturn. So Jupiter's great red spot is a storm, much like a hurricane. It's a little different because it's a high pressure region instead of a low pressure region. Well, it's high pressure at the top, so that would be low pressure. It's basically a hurricane, similar to a hurricane. It's a giant cyclonic storm driven by rising air, rising atmosphere, and it has existed for at least 3 centuries. We don't know how long it's existed because it's been around as long as we've been able to observe Jupiter well enough to see it. You know, Jupiter's great red spot has been around for as long as there have been telescopes. It's thought to be driven by the flows above and below it in the zonal flows. And so there's a current of air going this way below it, a current of air going that way above it. And it has been recently getting smaller. Hasn't gone away, but it is getting smaller. Might get bigger again. We don't fully understand it, but that is one of the things that it has been shrinking recently. It's bigger than the Earth. Its diameter is about 3 times the diameter of Earth. It's a high pressure region, while Earth storms are low pressure regions, but it's fairly similar. It's also kind of upside down. So Earth storms are where low pressure air is rising up and spreading out at the top. So we're kind of looking at the top of something similar to an Earth storm. It has been present for hundreds of years, and it's slowly shrinking. It may disappear in a bit, in a decade. It also might get bigger again. We don't fully understand it. So it has been present for hundreds of years. It was first observed in 1672. And it is, however, so this is the first observation. And it is slowly shrinking. So here you can see this is 1995, 2009, and 2014. You can see it's getting small. These are all Hubble observations. It may disappear in a few decades. We don't know. So Jupiter has these bands of color. It has a great red spot as a massive storm. You can see there's a gas flow below it, I think to the south of it, and then there's an opposing gas flow to the north, and that helps drive the storm. It's sliding across the easier side of it to spin. This is the Earth for scale. So it's about twice the size of Earth. I guess it's gotten this far. And the Hubble Space Telescope observations show it has been steadily shrinking between 1995 and 2014. You can see it's getting smaller. But so there's a great dark spot on Neptune. It's a massive storm on Neptune. It was observed in 1989 by Voyager 2, but by the mid-90s, it was gone. Hubble couldn't see it anymore. So this was the great dark spot on Neptune. It didn't last that long. But it has, fewer storm systems than Jupiter, but they're similar. So this large storm system, the great dark spot, has disappeared in more recent years. Saturn in 2011 had a global storm that circled the planet, as you can see here, and Cassini was able to observe it in detail. So this 2011 storm generated its own band, and it's seen in this sequence from Cassini. And it was observed in 2011 in visible light. And then here's an infrared image that was taken after the band had faded from visible light. So after the storm had faded away, there was still evidence in the infrared. Also, Saturn has enormous polar vortexes, much like Earth and Venus. So you may have heard about the polar vortex causing really cold weather on the news at some point. The polar vortex is just there's a current of air circling around the pole. And on Earth, when we talk about polar vortex in the winter, that's when that current dips further south and brings really cold air with it. So the polar vortex on Saturn, the northern, there's two different polar vortexes. This is the southern one, and this is the northern one. And the northern polar vortex on Saturn is shaped like a hexagon. It's like a perfect hexagon. Some sort of resonance or pattern caused it to have a hexagonal shape. So this is the six-sided jet stream known as the hexagon around the northern polar vortex of Saturn. It's very distinct hexagonal shape. This is Neptune's great dark spot. And Uranus also had a dark spot. Sorry, the dark spot similar to Neptune's. Thought it might be seasonal because Uranus had crazy seasons. So all of the Jovian planets have very complex atmospheres. The atmospheric structures are determined by the temperature and internal heat sources of the planet. And large storms have been seen on all the Jovian planets. So Jupiter and Saturn were known to the ancients. Uranus was discovered by chance, and Neptune was predicted from anomalies in the orbit of Uranus. The Jovian planets are large but not dense. They're fluid and display differential rotation. And the cloudlets have light zones and dark bands. And the wind pattern called zonal flow is stable. So the winds alternating in directions in the various zones, above and below each zone. And a similar pattern exists on Earth. It's something that's just caused by, if you have differential heating between the pole and the equator and a rotating planet, you get these bands. So Earth has from the equator 3. They're not super obvious on Earth, but we're in the middle of one. It's why the wind generally blows from west to east in the US. There's just more of them on Jupiter and Saturn. The storms appear with regularity. The great red spot on Jupiter has lasted for hundreds of years that we know of. And due to conductive interiors and rapid rotations, the Jovian planets have large magnetic fields. Jupiter, Saturn, and Neptune radiate more energy than they receive from the sun. So that is the end of chapter 11. And we will start chapter 12 on moons, rings, and plutoids. Basically, let me quickly stop sharing and share again because that solves that bug. This is the everything else category. So let's talk about moon rings and plutoids. So we'll start by talking about the large moons of the solar system. Moons basically get classified into three categories: large moons, medium moons, and small moons. Small moons are really small. Large moons are big and have significant properties. Our moon is one of the large moons. So the outer solar system has that number's more than 250 moons. That number is a little out of date. There are only 3 in the inner solar system. And there are 6 large moons in the outer solar system. These are comparable in size to Earth's moon. Jupiter has 4 large moons. Saturn has 1 large moon. Neptune has 1 large moon. Uranus does not actually have any large moons. There's a large number of medium moons, a decent number of medium moons around each of the planets, and a big number of small moons, which are probably captured objects. It's generally thought large moons formed with the planet. Small moons were captured on average, mostly, and medium moons could be either. So let's start with the first moons in the outer solar system discovered, the Galilean moons of Jupiter. These are the large moons of Jupiter. They were first seen by Galileo, hence Galilean moons. The closest to Jupiter is Io. It is volcanically active, covered in volcanoes, constantly spewing lava. Surface features last weeks. Then there's Europa. It has an ocean beneath its surface. It's covered in ice, but there's a liquid ocean underneath, and there's crab coming out. The recently launched mission, the Europa Clipper, is being sent to examine Europa and try and get a better understanding of what's going on underneath its surface. Because we'd like to understand how the ocean on Europa works. Because it's somewhere else in the solar system that has liquid water. And liquid water is a prerequisite for life, so we're interested in that. And then Ganymede and Callisto are older and have more cratered surfaces. So there's like water volcanism on the surface here. You get geysers that spew out water and resurface the ice. Ganymede and Callisto are older, they have more cratered surfaces. It's thought Ganymede may have an ocean, an underground ocean as well, while Callisto never fully differentiated, which makes it kind of interesting. But all the other large moons have. So all 4 Jovian planets have extensive moon systems, and more are continually being discovered. The Galilean moons of Jupiter are those observed by the astronomer Galileo. They're Io, Europa, Ganymede, and Callisto. So this is a list of the large moons of the solar system. Working from closest to the sun, and then for each planet closest to the planet out. The first one is the moon orbiting Earth. Size-wise, this is, I believe it's the 5th largest moon in the solar system. Then we have Io, which is a bit bigger than the moon. It's closest to Jupiter. It has an orbital period of 1.77 days. So it's going around quite fast. And its orbit is elliptical, so it gets kneaded as it orbits around Jupiter. It stretches and squeezes. Then we have Europa. The next moon out, it has a water ocean. Then Ganymede, which is the biggest moon in the solar system. It's bigger than Mercury. Callisto, which is the 4th moon of the first Galilean moon of Jupiter. Then Saturn has Titan, which is interesting because it has a thick atmosphere. And Neptune has Triton, which is very interesting because notice how the orbital period here is negative. That's because Triton orbits the wrong way around Neptune. So here is Jupiter with two of its Galilean moons. So here's the great red spot. Here's Io, here's Europa, as they orbit around Jupiter. So these are the orbits of Jupiter. They're drawn very round here. They're actually elliptical. But you know, Io, Europa, Ganymede. For every orbit of Ganymede, there are 2 orbits of Europa and 4 orbits of Io. So I remember that resonance right. And that keeps the orbits elliptical, that resonance, that pattern of 1, 2, 4, keeps the orbits elliptical and keeps them heated by tidal forces. So, interior-wise, Io is rocky and hot. It has an iron sulfide core, it has a rocky mantle, it has volcanoes spewing sulfurous lava all the time. Europa is thought to have a iron sulfide core, a rocky mantle, a water ocean, and an icy crust. Ganymede is thought to be somewhat similar. Again, iron sulfide core, rocky mantle, possibly water ocean, and an icy crust. And Callisto didn't fully differentiate. The heavy stuff didn't fully sink to the center. So it's sort of a mixture of ice and rock. So Io is the most volcanically active object in the solar system. 25% of its surface is warm lava. So a quarter of the surface is glowing lava. So it's warm lava. There are no impact craters on Io. They don't last. There's a large volcano called Pele. There's a bunch of different volcanoes on Io. There's a few dozen. And it is warmed by tidal heating. So the moon is stretched and squished by Jupiter's tidal forces. It has an elliptical orbit because of its gravitational interaction with Europa and Ganymede. And this is like, so when it's closer to Jupiter, it gets more stretched, and when it's further, it gets less stretched. And that kneads the moon like dough and warms it up. Like kneading a lump of clay, it warms the interior. So this is Pele. This is Olympus Mons. You can see them in comparison. Pele is also quite big as a volcano. You can also see it compared to the volcano Hawaiian Islands, which is appropriate because it's named after a Hawaiian deity. And so it has a very warm interior. It's heated up by the tidal forces from Jupiter. So it's being squished and stretched by tidal forces as it orbits around Jupiter. And this cycle isn't slow. It's happening every couple of days, because it orbits around Jupiter very quickly. Yeah, its orbit was 1.77 days, so every couple of days it gets stretched and squished like this. And that steadily warms the interior. So it's the densest of Jupiter's moons. It's the most geologically active object in the entire solar system. It has lots of active volcanoes, some of which are quite large. It can change surface features in a few weeks. And it has no craters. They just fill in too fast. It has the youngest surface of any object in the solar system. Surface ages are in weeks and months kind of thing, not thousands or millions of years. So it's the most volcanically active object in the solar system. Glow of intensely hot lava from volcanic eruptions, you can see basaltic lava flows, enormous plumes of lava throwing sulfurous material up, and all these eruptions. So this is an infrared image showing all the eruptions going. But why? So this is Io. Okay. I'm gonna have to go through and replace all these freaking videos. I think YouTube made a change. So this is Io. This is a quick video of Io. And volcanic eruptions continue to change the surface of Io, as you can see here. So these are some volcanoes on Io. It's very close to Jupiter, and it experiences gravitation. It also experiences gravitational forces from Europa and Ganymede. And the tidal stretching is huge, and that feeds the volcanoes. So this is a short video explaining how this works. So Europa, Ganymede, and Io are all in orbital resonance, and that keeps the orbits in stable elliptical orbits, which allows Io to get closer and further from Jupiter and heat up.
Tidal heating of Io and orbital resonances of the Galilean satellites are demonstrated. The satellite Io is revolving around Jupiter in an elliptical orbit. When Io is relatively far from Jupiter, there is a small distortion in its shape. When Io is relatively near to Jupiter, the tidal forces between Jupiter and Io are greater, causing Io to deform to a greater extent. Two red arrows representing the gravitational pull on the near and far sides of Io illustrate the deformation effect. When Io moves farthest away from Jupiter, the arrows are smallest and the difference between the two is small. When Io is nearest to Jupiter, the arrows are longest and the difference between the two is large. Now the simulation shows orbital resonances of the Galilean satellites. The Galilean satellites Io, Europa, and Ganymede are revolving around Jupiter. When Europa completes one revolution, Io completes two. As Ganymede completes one revolution, Io and Europa complete 4 and 2 revolutions respectively. The three satellites, Io, Europa, and Ganymede, show orbital resonance in the ratio 4:2:1 respectively.
And this orbital resonance gives a regular
When
tick.
Io completes 12 revolutions, Europa and Ganymede complete 6 and 3 revolutions respectively.
Keeps the orbits of all three of the planets elliptical. All three of the moons elliptical. Being elliptical causes tidal heating because they get stretched and squished more as they get closer and further from Jupiter, and that warms them up. It's thought this also contributes to the ocean on Europa and the internal temperature of Ganymede. So as Io orbits Jupiter, it gets squished and stretched. When it's far from Jupiter, it has small tidal bulges. When it's close to Jupiter, it has large tidal bulges. But why is it so elliptical? It's so elliptical because it's in resonance. There's a resonance between Io, Europa, and Ganymede. Every 4 Io orbits, there's 2 Europa orbits and 1 Ganymede orbit. So every 7 days, Io is opposite Europa and Ganymede. The tugs all line up, and this keeps their orbits elliptical. These add up over time, making all 3 orbits elliptical. Every 7 days, these 3 moons line up like this, with Io on one side of Jupiter and Europa and Ganymede on the other. And the recurring gravitational tugs make all their orbits elliptical, which leads to them being heated tidally. So Europa is a water world. It has an icy surface with a ocean of liquid salt water underneath. Liquid salt water with an internal heat source capable of producing, volcanic activities. Well, that's very similar to where we think life formed, conditions to what formed life on Earth. We think life on Earth formed first at like hydrothermal vents in the ocean. So that's part of why people really want to study Europa. It's smaller than the moon of Earth. but it has more water than Earth. Because it's got, a thick layer of water. It has relatively few impact craters. It has a relatively young surface. There are cracks on the surface. They're thought to be basically tectonic, and icy flows from the interior. This is similar to the Arctic Ocean on Earth. It's basically covered entirely in an ice sheet on top of the water. So if that ice sheet cracks, water can come out, resurface the area around it. You basically have liquid water underneath the ice, which can come up like as geysers or as cryovolcanism. So it's thought, solid center, liquid water, icy crust. And there's these cracks on the surface that are possibly tectonic. The plates of ice moving around. And driven by tidal stress that crack the surface ice. So tidal stresses cause parts of Europa's ice to slide past each other, similar to tectonic plates on Earth, but driven by different forces. These create these ridges and cracks. Let me see. And you can melt ice that collapses the center of the ridge. It's also warmed by tidal heating like Io, but not quite as extremely, because it's not as close. And it's thought to have a 100-kilometer thick ocean under an icy crust. And tides or upwellings of warm ice may sometimes create lakes within the ice, causing the crust to crack, and that explains this surface terrain that looks like a jumble of icebergs suspended in place. Europa has no craters. The surface is water ice with probably liquid water below, and tidal forces stressing crack the ice. Water flows out, and that resurface, keeping the surface relatively flat. Ganymede is the largest moon in the solar system. It has clear evidence of geological activity. So like old terrain that's heavily cratered and young terrain with few craters. It's thought that it may be driven by tidal heating plus heat from radioactive decay, because it's big enough to have a non-trivial amount of heat from radioactive decay. It has more craters than Io or Europa. It is an older surface, but it's icy, not rocky. Most of the moons in the outer planets have a surface that's primarily ice, not rock. It has signs of tectonic activities and icy flows. It's thought to have a liquid water interior, like Europa, and it has a magnetic field, which means it has a molten interior. So it's got some sort of liquid core generating the magnetic field. Ganymede is the largest moon in the solar system. It's bigger than both Pluto and Mercury. Now, this is not a small object. And it has a history that's similar to Earth's moon, but with water ice instead of lunar rock. And lastly, Callisto has an ancient cratered surface. It has an icy surface with lots of impact craters similar to the lunar highlands. Because ice in the outer solar system acts like rock in the inner solar system. And it is not fully differentiated, which makes it unique among large objects in the solar system. So Callisto did not have a case of all the heavy stuff sinking to the center, which means somehow maybe it was cooler when it formed or something like that. It's similar to Ganymede, but it has very heavy cratering and no evidence of resurfacing activity. It's just been sitting there getting whacked. And there are other moons as well. There's Titan around Saturn and Triton around Neptune are also large moons. So we can look at what happens on Titan and other moons. Titan is unique because it has a significant atmosphere. It's the largest moon of Saturn. It's the only moon with a significant atmosphere, which is comparable to Earth's. It's primarily nitrogen. It's similar in pressure to Earth's atmosphere. So you could go just hang out in lower gravity and similar sort of atmosphere. You need breathing apparatus because there's no oxygen. But because of the thick enough atmosphere and the lower gravity, Titan is actually a place where you could fly by strapping wings to your arms and flapping your arms, because the gravity is weak enough and the atmosphere is thick enough. And it's the only object in the outer solar system that's been landed on. The Huygens probe went to the surface. And another unique property of, well, the other thing you need is warm clothing because it's cold, is that it has lakes and rivers of liquid. It's the only place other than Earth that has liquid on its surface. And there's not liquid water, though. It's liquid methane. So it's quite cold. It's the only moon in the solar system that has a thick atmosphere. It's mostly nitrogen with some argon, methane, and ethene. It's been known to, for many years to have an atmosphere that's thicker and denser than Earth's is. That's mostly nitrogen and argon. Its cloudy atmosphere makes it impossible to see the surface. So this picture was taken from only 4,000 kilometers away. It's just solid clouds. So to see the surface, you need to penetrate the clouds with radar or send a probe down to the surface, which is both were done. This is an infrared image of Titan that penetrates the clouds, showing details of possibly an icy volcano. There are very few crude craters, which is consistent with an active surface. It's also one of the places that's going to have erosion because it's actually got like liquid moving around. And complex chemical interactions are occurring in the atmosphere because of methane and ethane and stuff getting hit by the sun. The Huygens probe provided a first look at Titan's surface in early 2005. It had liquid methane on the surface and rocks made of ice. So it's ice with liquid methane. That's, natural gas. And the Huygens lander took these images from the surface of Titan. So this is like the ground. These are drainage channels. These are some chunks of, rocks of ice on the surface. And because of trace chemicals in its atmosphere, it's quite chemically complex. So these aerosol haze, an ultraviolet optical haze layer, and an ultraviolet absorbing haze. There's a bunch of organic chemicals made from the methane in the atmosphere, making quite complicated atmosphere chemically. And there's some interesting chemistry going on. And here's the surface. It's the only object in the outer solar system that's been landed on. And it has these lakes and rivers of liquid methane. This is a radar image of the surface showing the lakes of methane on the surface. And here is a video that is also breaking. I'm going to have to replace all the videos in all my slides. So this is sort of a big showing a flyover over the hydrocarbon season lakes on Saturn's moon Titan. And it's the only other known place in the solar system with stable liquid energy. the heights are exaggerated is just to make it easier to see. So this is a radar image of Titan's surface. You can see these dark, smooth regions that there are lakes of liquid methane. This is another video that I'd like to play. I'm really sorry about the videos all breaking. This is something YouTube did.
And liftoff of the Cassini spacecraft on a billion-mile trek to Saturn.
We have a Doppler signature consistent with engine turn on.
So this is small. Also, but it has an ocean, which makes it weird. Here's that enormous storm. These are some of the many moons of Saturn. Well, I was wrong about how many moons Saturn has because they just added a whole bunch in March. It has 274 confirmed moons. They just added 128 in March. So the last of the large moons is Triton. This is the largest moon of Neptune. It has volcanoes that work on ice. So it's a mountain made of ice that spews liquid water like a volcano. The lava is water or a water ammonia mixture. It has an icy surface made of water ice, nitrogen ice, methane ice, and carbon monoxide ice. It's very cold. It has unusual surface features. It's weirdly smooth. It's thought that this might be due to tidal heating, radioactivity within it, some sort of weird icy greenhouse effect. We don't know a lot because it hasn't been observed very much, because it's in orbit around Neptune, the furthest of the planets, and there's been literally one probe sent to Neptune ever. So it's hard to observe things that far away. It's similar to Pluto, but it's larger. There's evidence of past geological activity. It's got a smooth surface. Pluto is similar to this. It's got a surprisingly smooth, even surface with few craters. And most interestingly about Triton is that Triton is in a retrograde orbit around Neptune. It's going backwards. So in general, all the other major large moons of planets all orbit in the same direction the planet rotates. Except for Triton. Triton rotates backwards compared to the orbit of the planet. All the other larger medium moons of Neptune orbit in the same direction as Neptune. Triton is just backwards. Its surface has very few craters, indicating an active surface. There have been nitrogen geysers as well as water geysers observed on Triton, contributing to these smoother surface features. So that was the 6 large moons of the outer solar system. Most are icy and show geological activity based on ice, as we have with rock in the inner solar system, and tidal interactions between the moon and the planet can also play a large role in the surface features. It is thought that Triton is actually a captured object from out in the Kuiper Belt, grabbed by Neptune, and that's why it's going the wrong way around. So it's thought that Triton is something similar, a bit smaller to something like Pluto, but traveling backwards as it rotates around, because it was captured, it was grabbed, it didn't form with Neptune. But there's still questions about how it could have been captured, because like we try and work out the way it would have been captured. It's like, why wasn't it destroyed? To slow it down enough, it would need an impact, and that impact seems like it would destroy it. But yes, so the moons in the outer solar system primarily made of ice on the surface. The ice acts like rock. It shows geological activity based on ice, as opposed to the rock we see on Earth. And in the inner solar system, and the tidal interactions between the moon and the planet can play a large role in its surface features, because you can have heating and other processes like that. I think, yeah, we have about 5 more minutes, so I guess I can keep going. We'll start on the medium moons. We may go over this again. So again, there's a lot of moons in the solar system. This number is out of date by a lot. It's more than 370 moons, because they keep finding more moons about Saturn. There's the 6 large moons, and then there's a decent number of medium moons. And then there's a lot of small moons. And it's thought that most of the small moons are captured objects. They're smaller things that get grabbed by the gravity of the planet and orbit around it. So here are some of the medium moons of the Jovian planets. So Saturn has a bunch: Mimas, Enceladus, Titus, Dione, Rhea, Iapetus, and Iapetus. Then Uranus has about 5: Miranda, Ariel, Umbriel, Titania, and Oberon. Uranus does not have any large moons. And then Neptune has Proteus. Jupiter has a couple as well. They just aren't on this table for some reason. So the medium moons of Jupiter, Almathea is about 200 kilometers across. It was discovered in 1892. It's the last satellite to be discovered visually. It has a red surface that's heavily cratered. It's covered in sulfur from Io, probably. And it has an old inactive surface. And Himalaya is about 170 kilometers across, and it's not yet closely studied by spacecraft. The moons of Saturn in natural color. So we have Iapetus, which has a really big, weird crater and a ridge around the middle. Mimas, Enceladus, which is volcanically active and is spewing out geysers of material. Rhea, Dione, and Titus. They're all fairly similar. There's a large crater on Mimas up here, so it looks kind of like Death Star. So here, Mimas, it's heavily cratered and it has a big, large impact. It looks kind of like the focusing dish from the Death Star. So it's known as the Death Star moon. Enceladus is one of the moons of Saturn that people are most interested in, because it has an icy surface with a mixture of old and young terrain, but most importantly, it is emitting plumes of water. So it has a subsurface ocean with salt in it. Because we've detected the salt in the plumes of water, and they're coming from the southern polar region. So Enceladus is one of the moons people are most interested in studying. Okay, and I think we'll stop there for today. We'll go back, or we'll continue with the medium moons next time and try and finish off chapter 12 next time. Have a nice day, and I will see you all next week.